Hi everyone, welcome to this new video, and today we will be discussing about an exciting topic, which is use of machine learning or artificial intelligence in finite element analysis. I'm sure you must be aware these days AI is everywhere, so why not finite element analysis? So let's begin. First, let's quickly clarify what artificial intelligence and machine learning actually are. This has nothing to do with finite element, it's just the basic introduction. Artificial intelligence or AI is nothing but capability of machines to perform tasks that typically requires human intelligence, such as problem solving or learning or let's say decision making. It has a broad spectrum, including but not limited to natural language processing, computer vision, robotics, you name it. A machine learning or ML is a subset of AI, and it focuses on algorithms that allow computers to learn patterns and make predictions based on data only, so without explicitly programming anything. And these are some types of machine learnings. The first one being supervised learning, then unsupervised learning, and third one is reinforcement learning. And in recent year, AI and machine learning, they are used everywhere, especially after ChatGPT came out. Fun fact, recently ChatGPT added functionality to create images, and I tried it out, and these images are generated by ChatGPT. But anyway, we are not going to go into detail of this AI or machine learning. Rather, focus of this video is how it can help us to do finite element simulations. In any typical finite element model, first we create a geometry, then let's say mesh it, apply materials, apply boundary conditions, define some analysis parameters, and finally run the simulation. Now this whole process, especially if your model is large, then running the simulation part is time consuming. There is no doubt about it. So one way AI or machine learning can help us is by reducing that entire time frame, and that comes under surrogate modeling or predictive analysis. In short, how it is going to work is we will run bunch of simulations first, then a model will train on those simulations plus their results, and next time if you want to run some other simulation, you don't even have to run the finite element simulation, but model will give you directly the results based on its prior experience of other models. So this is the main crux. We want AI to reduce our finite element simulation time. But there are some other things as well AI can do, like improving the accuracy of the results. It can generate high quality mesh. It can even suggest what will be the optimum mesh, so we don't have to do mesh sensitivity analysis. Machine learning can even dynamically refine the mesh in particular area, like in some high stress regions. Another area would be optimization of design parameters, where AI algorithm can explore multiple design parameters simultaneously, and it can give us the optimum parameters, such as let's say thickness of some particular flange, or even it can help in balancing multiple design goals. Next one I mentioned here is material modeling. For complex materials such as composite materials or viscoelastic materials, machine learning can use experimental data and predict material properties which can be given into finite element model. And of course, this is not the complete list. There are many more things we can utilize machine learning while doing finite element analysis, and that list is growing day by day. And because of these advantages, multiple software companies which make commercial finite element products are including these AI or machine learning tools into their product, such as Marc Mentat. If you have never heard of Marc Mentat, then Marc is the first commercial nonlinear finite element software, and Mentat is the name of its dedicated pre and post processor. This software is best known for performing complex nonlinear implicit finite element simulations, and I highly encourage you to check out this video, which explains everything in detail and shows how to run your first job in Marc Mentat. I will put the link of this video in the description box below. Now back to AI. If you open Mentat, then in Mentat GUI you can see this button which says AI ML tools. And these are some things Mentat can do, which I have listed down over here as well, such as you can generate parametric models, you can create design of experiments. This is basically to generate the data for machine learning model. Then all those models can be run in parallel. We can also create functional mockup units in Mentat. And finally, Mentat can export all the DOE results to software called ODYSSEE CAE. So what you have to understand here is Marc Mentat itself doesn't have machine learning models, but it can talk with another software whose name is ODYSSEE CAE, and that software is dedicated for machine learning. Of course, the parent company of ODYSSEE CAE and Marc Mentat is same, which is Hexagon, and that's why the seamless transfer of this data between two software is possible. But you do have to install the ODYSSEE CAE software separately. Hence, the thing Mentat can't do is to use machine learning algorithm for prediction or even for optimization, but that's not necessary because it can talk with software ODYSSEE CAE. Now just a brief intro about what is ODYSSEE. It is Hexagon's answer to AI ML, and it's specifically designed for engineers, and it's robust enough that it can work effectively with small datasets. You can go to this website to see more details about this software, and over there you can see it has 4 products. Out of that, our interest is ODYSSEE CAE. Hence you will need to download and install only this one product. And like many finite element softwares as well, we will have a separate name for solver and sometimes separate name for preprocessor. Similarly, in this ODYSSEE CAE, the GUI is called Lunar and it has 2 solver which are shown over here. Now we will see one very interesting example in this video, but before we go to example, I just want to briefly discuss the overall workflow of any particular example which we want to solve using machine learning. Now mainly we can have 2 goals when we use machine learning to expedite the finite element workflow. First, it's called prediction task, where we want to predict the result for specific input. For example, if you apply load somewhere on the part, what will be the maximum stress? We know what value of load we are going to apply and we want to know the stress. Or the other goal can be optimization task. This is at what input I will get specific output. So in the same example, let's say we want maximum stress to be 50 megapascal, then how much load I can apply without exceeding that limit. So in prediction, we know the load and we are asking, okay, how much stress it will generate. And in optimization, we are saying we know the stress and we don't want to go beyond that. So for that, what will be the maximum load I can apply? Irrespective of this, for both of these, this will be the overall workflow. We will of course start with Marc Mentat. First is we have to create the model. This will be the full model including materials, boundary conditions, mesh, everything. Then out of that model, we can define some quantities as parameters. In short, we are saying these quantities can change. Once you tell that to Mentat, Mentat can generate design of experiments and we can tell how many design of experiments we want. Let's say if we say 50, then Mentat will change those parameters in such a way that now we have 50 model where those parameters are varied in some range. Then all those models will be submitted for simulation. This can be done in parallel, so it doesn't really take much time. And then Mentat can extract the particular results you are interested in. For example, if you're interested in stress, Mentat will extract stress from all the results and finally will write files which ODYSSEE CAE can read. Those files will then go to ODYSSEE CAE. Here then we have to define if it is optimization task or prediction task. If it is optimization task, you will provide what is your target value. If it is prediction task, you will provide the input value and then ODYSSEE will run machine learning model and then write the results. Now next step is optional. Once you get those results, you can import them back into Mentat and run one more simulation just to verify if those values are correct. So for example, if you run 60 simulations first, created a dataset, trained some machine learning model in ODYSSEE CAE on that dataset, then you can simply provide any input and ODYSSEE CAE will give you what will be the finite element analysis result without doing that finite element analysis. But if you want to verify, you can do finite element analysis again using Marc Mentat just to check if it is correct or not. Now let's see one example. This is the example over here. This is going to be optimization example where we are trying to optimize the springback in metal forming. This bottom piece is die, this is punch, and this part over here is workpiece. You can see only workpiece has a mesh. These all other parts we will consider as rigid bodies. Just to simplify this example, this punch is going to come down in this direction, and when punch retracts, we will see some springback effect in this workpiece, because of which the final geometry will not be same as this, but it will be little bit different. First, I made list of which parameters which can change this springback. Definitely punch radius, die radius will play a part. Then the bend angle of the die, which is shown over here. Then workpiece thickness, the material of workpiece will also have effect. And in many cases, the temperature as well. This might not be the complete list, but these are just some major parameters which can affect the springback. For this example, for simplicity, we will choose only 2 parameters, which are punch radius and bend angle. Whenever we change punch radius, we will simultaneously change the die radius as well. That's why I considered both as a single parameter. Our aim here is after punch retracts, the workpiece should be in horizontal position like this. One way to do this would be randomly change all the parameters and run simulations until we get this flat profile, which is the trial and error method. Many people do that. There is nothing wrong with it. But when these number of parameters increases, then it is really challenging and very time consuming to follow this trial and error method. So the more efficient way would be use of machine learning. And how we can do that is we can create a model. We can define two input variables. One will be this bend angle over here, and one will be this radius. Then we will change these input variables, and let's say we run 50 simulations with different values for these input variables. And every time die will come down, again it will retract, and once it retracts, we can measure the displacement of this node, which we want to be exactly minus 20, so that this workpiece will be flat over here. So after 50 simulations, we will have 50 values of this Y displacement. Then we can train machine learning model using those 50 Y displacement values and these 50 input variable values. And then we can ask the model at what input variable values I will get Y displacement to be exactly minus 20. And that would be our answer. So enough with PPT now. Let's actually open Mentat and see how to do this. As I always say, first thing is set up your work directory. I have created one folder over here on the desktop named metal forming, which is empty right now. And this folder we will set up as work directory for Mentat. To do that, file, current directory, path over here and choose. Now whatever we do, everything will be created over here. As this is the first video about machine learning, I wanted to keep it simple. So I chose this example because it is already there in Marc. What you have to do is go to help and users guide. And if you scroll down over here, this one is example number 129. You can find all the information here, but anyway, we are going to go through this process step by step in this tutorial. We will not be modeling this from scratch, but rather than that, just go down over here and you will see two proc files are mentioned over here. For this video, I am assuming you are familiar with Mentat and what is proc file or how to create those parameters. If you're not, please comment down below and I will create a separate video just for these proc files. But for this video, what you can do is click on this play button and say OK. And what this will do is copy this proc file into your current directory along with some other needed files. So if I go back to that folder, now we see there are 3 proc files and 1 Marc model file. Now before running this proc file, let me open this Marc model file. This is that model. So everything is defined over here. This is the material which has plasticity in it. Then boundary conditions are defined, load cases are there, even job is also created. Only 2 things are missing over here, which is this radius and bend angle. So when we run that proc file, it is going to take this model and then add radius over here and also add that bend angle. Let me close this. Let's open this proc file as well. This is how that proc file looks. So it is opening the model and then adding radius and bend angle. You can adjust the number of data points over here. It says 60, but let's say if you want to change it to 40, just save it. And now if I call this proc file in Mentat, just say start. Mentat already created 40 number of experiments. That means it is going to change radius and bend angle and create 40 simulations. Let me go back to that folder and you can see over here 40 folders will be created and each folder will have Marc input file. And if you check this input file in each folder, for every input file the bend angle and punch radius values will be different. So let's see, let's wait for completion. You can see over here these radius and bend angle is different for every time. So we did not do anything explicitly here. We just told Mentat what should be the variable parameters and how many number of experiments we want to run. Almost done. You can see over here, these are the 40 models and each are kept in separate folders. Otherwise it will be one giant mess. And now we can run all those simulations in parallel. So I'm choosing 5 jobs at a time and then just say run experiments. You can track the status of all jobs over here. And if I go back to that folder, let's see the folder number 1, job is submitted. And now we have the result file ready. Done. If I go back to that slide, what we just did is we set up the model, we defined the parameters. You can see parameters are over here, radius and bend angle. Then we generated different design of experiments. We decided to go with 40 and we ran all the simulations. Next step is extracting the specific results. Now result, we are interested in the displacement, that also Y displacement of this particular node. And for extraction, again we have to take help of one proc file. That proc file is already selected over here and it got copied in this folder when we copied all the initial files. So springback post, this is that proc file. And if you notice, there is one Excel sheet named springback. If you open this Excel sheet, you will see all different 40 values of radius and bend angle. These are all those 40 values. So let me close that and let's extract the results by clicking over here. Now Mentat is opening each and every result file and storing the data for Y displacement of that particular node. And finally write files for ODYSSEE, which can be done by export results. And once you do that, two files will be generated over here. One will be springback input and one will be springback results. These two files will provide all the necessary data to ODYSSEE. You can open it. It is again just the same thing, input values. And here it will have Y displacement. You can see over here the Y displacement, it's around 20 but not exactly 20, and we want to know what input parameters will give the displacement of exactly -20. Now we have to open the ODYSSEE. You can just directly open that from start menu, or you can open that from Mentat as well. We just have to go to this AI ML tools and ODYSSEE. This is ODYSSEE. It brings us to over here. So first step is to import the files. But before doing that, we have to create a project. Let me again say metal forming. And here too you have to choose working directory, which I'm choosing same as our Marc working directory. So select folder and say OK. Now we have to import two files. First we will choose X base cases and then import CSV and choose the springback input file. Say open. Here, let's say if you change your mind later on and if you don't want to include some data points, you can just deselect them. But I am keeping all 40 points. Then go to Y data and import dataset from CSV and choose the results file. And then click on this validate data configuration. Say OK. Now we will not go into detail of how ODYSSEE works or what different models are available, but overall you can follow the workflow which is on the top here. First we started by creating a project, then we imported data. For now sensitivity we will skip because we don't need it, and directly we will go to interpolation. Here ODYSSEE will create predictive model. To do that, first click on this gear icon where you can choose from different solvers, different interpolation methods, but I am going to keep everything default for this video and just click on run. Once interpolation is finished, say OK. And now we will move to optimization. This will be our last step. We will not go into animation or user script. Here we will get our results. Now what we have to tell ODYSSEE over here is our target value. We want displacement to be -20. Again, let's click on the gear. The first thing is configure parameters. We don't want to change anything over here. And let's go to define optimization problem. Here we will add the target. You can name the target as, let's say, displacement, and select target type as value at, and this value should be -20. For this example, we are going with single target, but you can add multiple targets as well over here. And third one again, you can leave it as default. Say OK and click on run optimization. This is the main step. It is trying to find out at what bend angle and at what radius we will get exactly flat specimen. And these are the magic numbers. So radius should be 3.0816 and bend angle should be 2.67314. And you can see with these value, our displacement is very close to -20. The highlighted blue line over here is the optimized value. You can either directly believe it or we can validate this result as well. For that, we have another proc file ready for you. Remember earlier we copied this proc file. Now we will copy this verification proc file. Again, click on this and say OK. Once you click that, this verification proc file will be copied to the folder. That means your current directory. This is that verification proc file. So let me open this, and here are those values. So by default, there are some values. These ones, they got it. We can replace these values with our values, which are radius is 3.0816. and bend angle is 2.673. So these are little bit different than what it is shown in this example, because here I think they used 60 simulations, we are using 40. But I'm hoping we will also get displacement close to -20. I change these values, let me save it, and then I will run this proc file. Now only one job is created. Our value is -20.1. Compared to value given over here, their value is much better, I would say, because they use more number of simulation to train the machine learning model. But I would say our value is also pretty close. That's all for this video. As I said, I will create another separate video where we will go through how to create those .proc files and how to set different parameters which is needed to use this AI ML tool in Mentat. And after that, we will see some more examples using this particular tool. Mentat has a capability to use reduced order model with the help of functional mockup unit. That is another huge topic. So maybe I will create another dedicated video just for that. So thank you for watching, and I will see you in the next one.